Good afternoon, everybody. Let's get started with the class. For announcements, check the upcoming assignments posted on Canvas. Those are out there with their due times and due dates. Be sure you check the time that they're due. Some assignments are due at different times during the day. That's all posted on Canvas. Pre-Lab 1 is coming up, Quiz 1 is coming up, and Homework 1 is coming up. And if you have any questions about those, stop by office hours right after class, and I'd be happy to talk about those. Or check out Slack when you start working the assignments. And you can click on the invitation link on Canvas, get on Slack, and post questions there. And that's where I'll answer questions if you have any. So let's see. We finished up last time talking about circuit variables, and now we're going to go on to basic circuit analysis. Okay, so we're going to talk about circuit analysis fundamentals. Now, the beginning of this class is largely review if you've done a lot of circuits work before. But some of you may be new. This may be new to some of you. And so I like to go through and show how I apply these analysis techniques like KVL, KCL, Kirchhoff's laws. And so we're going to go through those. And rapidly in the next couple lectures, we'll get to some new and more challenging material. But I definitely want to hit these topics because they are very important for the material for the rest of this class. Okay, so let's start talking about Kirchhoff's laws. We'll start with Kirchhoff's current law. So here's a circuit, and I have my fictional circuit elements A through E. Doesn't matter what they are. Kirchhoff's current law applies to any components that are these circuit elements. And so to talk about Kirchhoff's current law, we have to define the concept of a node. So a node is the entire connection between two or more circuit elements. So for example, this is a node and this is a node. So the node on the left is the entire connection between two circuit elements. The node on the right, the green node, node 2, is the entire connection among these four circuit elements. So when you think of a node, think of the node being not just a dot at a junction of wires. Think of the node, for the purposes of KCL, being this entire connection, that entire conductor between circuit elements. Let's concentrate on node 2. So I've highlighted node 2 in green here. And to talk about KCL, to write an equation, let's define some currents. So I've defined currents I1 through I4 here. I1 comes in through element B, I2 goes out through C, etc. I've arbitrarily defined the numbering and I've arbitrarily defined the reference directions. Okay, so for KCL, if you're given reference directions for currents, use them. If you're not, you can choose your own. Okay. So Kirchhoff's current law can be expressed in three ways. And here's the first of the three. The sum of currents entering a node is 0. Okay, so if I add all the currents up, entering a node, this node 2, the sum should be 0. So here I have I1 entering. I'm going to add that into my sum. I have I2 leaving, so I got to do something about that. I have I3 entering and I have I4 leaving. Now I want all of my currents, my reference directions, when I sum them according to KCL number 1 here, I want all the currents entering that node. So what I'm going to do is I'm going to flip the reference directions of I2 and I4 and just call them negative I2 and negative I4. You can do that, that works. And so my sum of currents entering will be I1 plus a negative I2 plus I3 plus a negative I4, and that sum equals 0. So that's one of the three ways. The second of the three ways is you can sum the currents leaving a node and set that sum equal to 0. So I have, let's see, I2 leaving and I4 leaving, but I have I1 and I3 entering. I can flip those around flip I1's reference direction around, call it negative I1, flip I3's reference direction around, call it negative I3, and sum the currents leaving. Negative I1 plus I2 plus negative I3 plus I4 equals 0. Okay. And so these are the same two equations, right? I just multiply both sides by -1 in the top equation, I get this bottom equation. Number 3, the third way to express KCL is the sum of currents entering a node equals the sum of currents leaving a node. This is a different way of visualizing KCL, Kirchhoff's current law. Okay, so if I go back to my original definitions of currents without flipping the arrows, I1 and I3 were entering, I2 and I4 were leaving. So I1 plus I3 equals I2 plus I4. This is the same equation. If I move the negative I3 and negative I1 to the other side, or negative I2 and negative I4 to the other side of the top equation, I get number 3, that equation number 3. Okay, so you can visualize Kirchhoff's current law if you use the fluid flow analogy. So imagine you have a copper pipe here and you have fluid flowing through water flowing through that copper pipe, right? You can imagine that this is a junction. This node is a junction in that copper pipe. So, and there's no storage, there's no expansion, there's no like balloon in there that can store water. It's a rigid pipe. So all of the fluid coming into this node must leave that node in terms of rate, right? If you have 3 gallons per minute coming in, then you must have 3 gallons per minute leaving somehow, right? Because there's no water storage here. There's no charge that can accumulate in there from flowing current. So you can visualize KCL using the fluid flow analogy. So that's Kirchhoff's current law. Let's talk about Kirchhoff's voltage law. To talk about Kirchhoff's voltage law, we need to define a loop. Okay, so here's a circuit. I have circuit elements A, B, C, and D, and I have a couple terminals here. So these circles at the end of wires, those are just 2 terminals. That normally denotes you could connect something there. Maybe it's a sub-circuit that connects to the rest of a circuit. Maybe you connect a voltage source there, something like that. But this is the entire circuit for now. We're going to work with this circuit. So a loop is any closed path around a circuit. Okay. So for example, let me define loop 1. I've just picked a starting point. You have to end at the starting point, and I've picked a direction. It doesn't matter which direction, but this is what I'm calling loop 1. Now a loop does not have to be a closed circuit. It just has to be a closed path. For example, I can define loop 2 as this loop, this blue loop. So loop 2, I've started up here at the upper right. I go across D, I go across C, and I jump between these 2 terminals from bottom to top, and I end at the same starting point. I end at the starting point, so that makes it a closed path, but it's not a closed circuit because I have a gap here. I have 2 open terminals. That's okay. You don't have to just run a loop, define a loop around these kind of inner circuits here or inner paths. You can have loops go around, let's say, the perimeter of this circuit. Okay, so here's starting up here at the upper center, cross D, I cross that terminal pair, cross A, cross B, back to the starting point. That's a loop. So those are the loops that we're thinking about. So someone asks, is it correct to think that loops contain nodes, but nodes don't contain loops? Yeah, I guess I would describe it as a loop starts at a node, okay, and it goes to another node, usually across a component, or it goes to another node across a gap or a pair of terminals like this. Okay, so you're going from one node to the next. So you could say you could actually define your loop by saying go from this node to this node across this component. So let's apply Kirchhoff's voltage law to a loop, or many loops, a few loops. So here's that circuit. I'm going to define voltages across each one of these components, VA, VB, VC, VD, okay? And I've arbitrarily picked polarities. If you're given polarities, use them. If you're not given polarities, you can make them up. You will get the right answer with KVL. Okay, now if the variable you're looking for has the opposite polarity of mine, you're going to get -1 times mine. That's okay if we haven't defined polarities, because that means the same thing. If you have a variable with a polarity, multiply it by -1, switch the polarity. That represents the same voltage. KVL is this: the sum of voltages around a loop is 0. Okay. So we have to talk about, what does that mean? How do you sum these voltages together? You have these polarities, not just variables, but you have these polarities. I'm going to show you a way I like to do this. Okay, so let's do loop 1. For loop 1, I'm just going to pick a point on the circuit. I'm going to pick a node. I'm going to start there, and I'm going to go just define a loop, go around a loop. I'm going to pick a direction. So KCL will be valid around this loop 1 if I start at any node, any point along that loop, and I go in either direction. KVL will give me the same answer. Okay, so what I chose to do is I started at the lower left. I went around clockwise, and you have to end up at the same point where you started. And you're going to add voltages when you go from one node to the next node, or what I say is you're going across a circuit element. Okay, here's the way I like to write a KVL equation. I'm going to start here at the lower left, and I'm going to follow this process. When I follow a conductor and I hit a component, I'm going to write the sign of the polarity that I encounter, in this case, a negative sign. Okay, and then I'm going to write whatever value or variable is in between the polarity signs, symbols here. So in other words, I'm going to say minus VA. Okay, and whenever I hit the next component, I'm going to say plus, because I hit a plus, VB. And here, minus VC. Back to the starting point. When you get back to the starting point, don't forget to write equals 0. So minus VA plus VB minus VC equals 0. So that's the KVL equation for loop 1. Let's write a KVL equation for loop 2. So I've started it at the upper right. I chose to go counterclockwise. That's okay. And so let's follow that same process. I'm going right to left here. I hit a plus. I write plus VD minus VC minus Vx, right? I'm going between two terminals. There's a voltage defined between these two terminals. So minus Vx equals 0. Okay. Don't be bothered when there's a voltage across two terminals. Some people are, some people aren't. But it's like having a 9-volt battery sitting on your desk, right? There are two terminals coming out of that 9-volt battery. Nothing's connected to the 9-volt battery, and there's 9 volts across that battery. So that's okay. You can have a voltage across two terminals that aren't connected to anything. But so this equation will be plus VD minus VC minus Vx equals 0. Okay, that's how I like to write that equation. I can write an equation for loop 3. So start here, minus VD plus Vx minus VA plus VB, back to the starting point. Don't forget, right, equals 0. Okay, so I like to follow that approach where when I hit a plus, I write a plus. When I hit a minus, I write a minus. Now, some folks are bothered by that. Some professors, some TAs teach it differently. They teach it exactly the opposite of the way I write it. And what they would argue, and they're right, I just think it might be prone to mistakes, is, okay, so if I go, let's go over here to circuit element A. If I go from the negative side of VA and I move to the positive side of VA, I'm going up in potential. So some would have me write plus VA, okay, because I'm going up in potential. And you could do that if you follow that consistently around. The problem comes in when I have negative voltages. Some people, including me, get the numbers mixed up, get confused whether they're going up or down in potential. They like to think, am I going up and down in potential? I'm going to add in when I go up, I'm going to subtract when I go down. But like if VA is -6 volts, you can have a negative voltage VA here. That's just fine. So they would say, okay, I'm going up in potential. but wait a minute, that's negative, so I'm going down in potential. So do I write plus a negative to go down in potential? Do I write minus the negative potential to go down? So it gets a little confusing. You can confuse yourself, I think. Um, so the way I teach it is if VA is -6, let's say it wasn't a variable, it says -6, you would write minus -6. If VB is +5, plus +5. If VC is -2, I would write minus -2. Okay, so I probably gave numbers where I would violate KVL. Don't hold me to that. But usually what you're doing when you are writing KVL equations is you either have a loop where you have all known voltages and one except for one unknown voltage, or you might have to write a system of equations. Okay, so you might have maybe two unknown voltages in a loop, and you have to write maybe two equations with two loops to solve for the unknowns. Okay, but that's my summary of KVL. I think that I always follow this approach. When I hit a plus, I write a plus. When I hit a minus, I write a minus. Following that plus or minus, I write the value, whatever's in between those polarity symbols, and I think you can't go wrong. Okay, so let's give that a shot. Let's try a clicker problem. So here's a problem. You have the circuit. I have A, B, and C. I've defined two voltages numerically here, and I have an unknown variable. I've put polarity markings here. So with those polarity markings, you have to use those. You can't choose your own. So let's give this a shot. Let's talk about this solution. So we have a loop. There's one loop here. We want to write a KVL equation to solve for VC. I can start at any point on this circuit or any node, and I can go in either direction. I can start up here at the upper right. I can go left. I can say plus a -2 -6 plus VC equals 0. I can go to the other way. I can say minus VC plus 6 minus a -2 equals 0. I'll get the same answer. I could start at the left side, go down, -6 plus VC plus -2 equals 0. You'll get the same answer. So in this case, I chose to do this. I said plus 6 minus -2 minus VC equals 0. And you could try those different combinations of starting at different points and going either direction. You'll get the same answer. Okay. All right. So if you're not enrolled in the clicker, please do so, because that's how we collect the clicker questions. And don't worry if you've missed one or two of these. You just have to answer during half of the clicker sessions to get full credit for that homework. So it's no big deal if you miss one or two clickers. Okay. All right, let's talk about a concept called network reduction. Okay, you've heard of series and parallel combinations of components, I'm sure, like combining resistors in parallel or capacitors in series. We're going to talk about that. But that's all part of what we call network reduction. Network reduction takes a complicated circuit, relatively complicated circuit, and converts it into an equivalent simple circuit, usually for the purpose of easier analysis, but sometimes for practical reasons, like if you have you need a 500 ohm resistor and you have two 1000 ohm resistors, you can create a 500 ohm resistor. Okay. So an example of this is taking this circuit where I have these circuit elements, and I've exposed two terminals here, so terminal A and terminal B. And what I can do is, with some form of network reduction, I can create a simple circuit or even a single component that behaves the same way as the original, more complicated circuit. Okay, so terminals A and B behave like, or I should say between terminals A and B, the circuits behave the same way as seen from the outside. And by behave the same way, I mean this. If I took this circuit on the left, I put it in a box, I expose two wires, I call them A and B. I take this equivalent circuit that I've reduced down using network reduction. I put it in a box. I put this circuit in the box. I expose two wires A and B. And if I give you a voltmeter, an ammeter, a power supply, whatever, an oscilloscope, and you apply a voltage, you apply a current, you measure voltages and currents just at terminals A and B, you wouldn't be able to tell the difference between those. They would behave the same way. Series and parallel combinations of circuit elements are one way to do this network reduction. So let's talk about series and parallel combinations. Okay. Now, you may have done this before. Sometimes some people can just look at a circuit. They can look at two components and say, oh yeah, they're in series. Oh yeah, they're in parallel. Okay. And I do that. And I'm sure many of you do that. But there's sometimes when you look at a circuit and you just can't tell, so fall back on these definitions. You'll see, I think in a homework assignment, there's one problem where you go, I can't really tell which are in series and which are in parallel. Follow these definitions for series and parallel. For series, circuit elements are in series when the same current flows through them. So if I have two circuit elements, A and B, and I imagine, I don't even have to have a current, I just have to imagine a current flowing, let's say from left to right through A, will that current necessarily also flow through B? Yes, because there's no place else for it to go. So any current through A will flow through B. So these circuit elements are in series. For parallel, circuit elements are in parallel when they connect to the same two nodes. So if I have two circuit elements A and B that connect to the same two nodes, they're in parallel. So these are these circuit elements. Remember, the node is the entire connection. So circle the whole entire wire here at the top. That's one node. Circle the whole entire wire, this connection. That's another node. A and B connect to those same two nodes, and therefore they are in parallel. And for your homework problem, if you can't quite see it, you might try circling your nodes. Circle them in different colors. Circle them in red, circle them in blue, and you'll see, oh, A and B connect between red and blue. They must be in parallel. Sometimes it's not so obvious. So let's give this a shot. Let's talk, or let's do a clicker problem with series and parallel elements. Okay, so here is a circuit. I have 8 circuit elements. They're all connected together like this. So answer, circuit elements number 1 and number 2, are they in series, parallel, or neither? Here's how I would work this problem. I want to determine if 1 and 2 are in series, parallel, or neither. So I ask myself, if I had current flowing through circuit element 1, would that same current flow through circuit element 2? And I would say yes, because if current flows out of circuit element 1 to the left, it would also flow into, or to the left, it would flow into circuit element 2 to the right. Okay. Now you say, well, on the other side of 2, we have current going up through 3 and maybe up through 4 and up through 5. Well, we're not really considering those. And if you look at the right side of 1 and 2, it's kind of hard to tell. Well, is the same current going into the left side, out of the right side? Well, yes, but it's easier to see if you look at the left side of the circuit. If current comes out of 1, it'll go into 2, following my cursor there. Or the other way, if it goes out of 2, it'll go into 1. The same current is flowing through them. Also, you ask, do they connect to the same 2 nodes? Well, no, they don't, because I have a node over here. I have a node up top, this top center node. That's where 1 connects. Here's another node down here at the bottom center. That's where 2 connects. And 1 and 2 do not share nodes on their right side. So that's the way current could flow if it were to flow. So these are in series. Okay. All right, try this one. 5 and 7, series, parallel, or neither. So take 30 seconds. See if you can figure that out. And think about those rules. If current flows through 7, does it necessarily flow through 5, or do they connect to the same 2 nodes? All right, so let's stop here. So circuit elements 5 and 7. So ask yourself, if current goes through 7, does it necessarily go through 5? So if current comes up through 7, it also goes through 6. Well, some of that current might go down through 5. It could go along this direction, go down through 4, right? Imagine fluid flow through these pipes. We're calling wires here for the fluid flow analogy. So the same current that goes through 7 doesn't necessarily go through 5. Okay. And do they connect to the same two nodes? Well, 7 connects to this upper right and lower right node, and 5 connects to the center top and center bottom node. So those are two different nodes, right? The 7 connects to the blue nodes, 5 connects to the green nodes. So neither series nor parallel. Okay. Now, someone had a specific question. So right now, I would say 3 and 4 are in parallel. I would agree. They connect to the same two nodes, right? 3 and 4 connect to the green nodes. So yes, they're in parallel. What if another element was in the top wire between them? Yeah, so if I could possibly annotate here, let's see if this works. So if I draw, I think you're talking about like right here, I put a circuit element, I call that 9, right? Would 3 and 4 be in parallel? No, they would not be. And the reason I say no is because if you look at the nodes to which 3 connects, you get this node, right, up here, and the bottom node. And then which nodes does 4 connect to? Well, 4 shares that bottom node with number 3, but it's a completely different node. 3 does not connect to this node here. Okay, so at the top, 3 and 4 do not share a common node. So would they be series, parallel, or neither? Neither, because the current that came out of 4 wouldn't necessarily go down through 3. Okay. Okay. See if I can clear all drawings. So someone says, so essentially a connection cannot be interrupted. Well, look at the definition of it. Yes, but I would describe it as define your nodes, circle your nodes. So when you want to define a node, so here, look at this top node. If I were to circle that top node there, annotate. So I would say this is the node, right? You can put that circle there, that outline. You know, between 7 and 8 down here, this is a node. So circle the nodes. And if I put a circuit element here, right, and then I circle the node, right, or nodes, I would say this is a node, right, that blue node, which is completely separate from this green node, right? So yes, the node, when you define a node, start on the wire, go out until you hit a circuit element, and that's where the node ends. Okay. Yeah, that's good. Good question, because sometimes once you visualize this, right, you can see it, and then, but right before you visualize it, it's not visualizable. Okay, let's try this one. So circuit elements 3 and 5. Series, parallel, or neither. Take 30 seconds. Yeah, I like circling nodes. I like taking a highlighter, just, print it out or get on your tablet and circle the nodes or highlight on your tablet or whatever you're working on. I like highlighting them in different colors when I can't see is something in series, parallel, or neither. I really do highlight them to try to visualize between which two nodes is each circuit element connected. Okay. All right, so let's work this one. So I just show the answer. So 3 and 5 connect to the same two nodes. Both 3 and 5 connect to the green nodes. Okay, so they're in parallel. And if you look at the current through 5, it doesn't necessarily all go through 3. Okay, and how about 6 and 8? Let's try this one. I think I have 1 or 2 more of these. So for 6 and 8, here's what I would do. I'd say, okay, do they connect to the same two nodes? No, 6 connects to this upper right node, 8 does not connect to that. So they don't share common nodes. And then I ask, well, if current were to go through 6, would that current also go through 8? Well, yes, right? Because that current, although 7 is between 6 and 8, the current that goes through 6, if I were to paint an electron, you can't do that, but if I were, and or a positive charge, because we're electrical engineers, if I were to paint a positive charge and watch that charge flow, that charge would go down through 7 and then through 8. So that same current would go through both 6 and 8. So they are in series. Okay, I think I have one more here. So try this one. 3, 4, and 5. Series, parallel, neither. So yeah, let's see, someone asked to explain the previous question. I'll do that. So we finish this one. Okay, so let's talk about this one. So 3, 4, and 5, you ask yourself, does the same current go through all of them? No, the current that goes up, if I were to imagine a current going up through 3, it would split, it would go through 1. All of that current wouldn't go through 4. All of that current would not go through 5. If I circle the nodes of this circuit, I would notice that I have these, green nodes, top and bottom. And 3, 4, and 5 all share those two nodes, right? They all connect to the same two nodes. And so this is really there to show that you can have not just two circuit elements in series or two circuit elements in parallel. You can have 3 or more in series or parallel. So let's go back to let me explain this other one. Someone had a question about this one. So why are 6 and 8 in series? Because if I have current flowing through 6 to the right, that same current flows through 8. Okay, there's no place else for that current to go. Now, if I had a branch here, if I had like a branch off of 6 and it went to some other part of the circuit, and that current out of 6 could go to the right, then then 6 and 8 might not be in series. Okay. So let's see. Someone says because the left-hand side of 8 hits 2, while 6 hits 1. Well, yes, like 6 is connected to 1 on the left, but it's also connected to 3, 4, and 5. And here's the thing, you don't have to prove it. You don't have to prove, for example, that the current coming to the left out of 6 also goes into 8 from the right. You don't have to prove that. If you can find one case where you say, yeah, well, current leaving 6 to the right goes down through 8, or the current leaving from the right, to the right through 8 also goes through 6, that's sufficient to say they're in series. Okay. And by the way, 6, you asked about 7. 6, 7, and 8 are all in series. Those 3 are in series. 7 and 8 are in series. 7 and 6 are in series. 6, 7, and 8 are all mutually in series. 6 and 8 in series. So, what's the so what? The so what here is there are certain rules. That's not the right word. There's certain approaches that you can use when you have, let's say, resistors in series or capacitors in series. There's certain approaches you can use to either combine them or figure out what voltages are across them, given a voltage across a series set. And we'll talk about that. But like if I just cared about 6 and 8 and I wanted to apply, an approach, I could say, yeah, if the approach applies to series resistors, then I could apply that approach to 6 and 8 without even considering 7. Okay. All right. And like if you can disprove, if you disprove it's not in series, if you prove that a pair is not in series, then it could be parallel and it could be neither. So I guess you'd have to disprove 2 of the 3 to get the third. So that's another way to think about it. Okay. And 3 and 5 are in parallel. So 3 and 5 are in parallel because they share the same two nodes. So here 3 and 5, right? They connect to the same two nodes. So 3 and 5 are in parallel. 4 and 5 are in parallel. 3 and 4 are in parallel. 3, 4, and 5 are all mutually in parallel. They all connect to the same two nodes. Okay. So if you want, stop by office hours and I can make up some more examples and show you those. We can talk about that more. Okay. All right. So let's do this. So those are the basic analysis techniques. Those are kind of the foundation for talking about other analysis techniques. So what we're going to do now is talk about a specific circuit element, not just a box with a letter in it. And the first circuit element that we're going to talk about specifically is an electrical source. So let's talk about electrical sources. Okay. Sources are circuit elements, and they maintain a voltage or a current in a circuit. So you could have a source that maintains a specific voltage, or you can have a source that maintains a specific current. There are realistic examples of sources I'm sure you're familiar with. We have ideal sources, but those ideal sources within a limited range, within a limited application, can represent realistic sources. So for example, batteries. Right? Batteries are an electrical source that largely maintain a voltage. Solar panels, right? That's an electrical source. Battery chargers, that's another source. I'll show you those can be a current source. Signal generators, like an RF signal generator or a function or waveform generator that you have in lab. That's an AC source mostly. And one thing that's not so obvious is that sources can supply power. That makes sense, like a battery supplies power, but a source can also absorb power. So, for example, a solar panel powering a circuit. You put up a solar panel, you're powering a amateur radio, and probably with a battery connected also. But that solar panel would be supplying power to a circuit. Okay. Sources can also absorb. For example, a battery is a source, but if it's a rechargeable battery, you can charge that battery, and so that source is now absorbing energy, absorbing power. So let's take a look at what types of sources we're going to talk about. So I've got this kind of quad chart here. We're going to talk about voltage sources and current sources. Voltage sources maintain a voltage, current sources maintain a current. And for each of these, there are two types that we're going to talk about. There's an independent source and a dependent source. Dependent sources are also called controlled sources. So these are going to be synonyms in this class. Each type of source has its own schematic symbol. Okay, so a voltage source is a circle with polarity in it with a specified voltage. Current source is a circle with a reference direction in it with a specified current. So if you look at the circles, the difference is polarity or reference direction arrow. Dependent or controlled sources will be viewed as diamonds, will be written down as diamonds in a schematic in this class. So when you think dependent, think diamond, dependent, or controlled. Okay, so this is a dependent voltage source. This is a dependent current source, and I'll explain what that means. Those sources, those dependent sources, depend on other voltages or currents in the circuit. So let's start with an ideal independent voltage source. An ideal independent voltage source maintains a specified voltage across its terminals. Here's its schematic symbol. Here's its specified voltage. So you'll see me write VS a lot, and maybe VS equals a number or maybe just a number. So this means that this voltage source maintains this specified voltage, right, with this reference polarity across its terminals. So if I have a 12-volt source with this polarity, I'm going to have 12 volts across these terminals. That's what that voltage source does. If I connect a component, a circuit element X, then voltage source VS has caused 12 volts to appear to be across circuit element X with that polarity. So this name means something. Each term means something. So ideal means that this voltage source maintains a specified current. Voltage. This voltage source maintains a specified voltage, not current, voltage, no matter what is connected to its terminals with an asterisk, like within reason, unless you have some kind of contradiction. For example, if I have this 12-volt source and I connect anything here, capacitor, resistor, a motor, right? This is an ideal source, so I'm going to have 12 volts across that component. Okay, the asterisk means, well, unless I short, a short means to connect a wire between two terminals. So if you short two terminals, you're connecting a wire. Think ideal conductor in this case between the top and the bottom terminal. If I short the top to the bottom terminal, that means I have 0 volts between those two because they're the same node. The voltage between a node and itself is 0. So you can't have that. You can't short a voltage source and have it mean an ideal voltage source and have it mean anything. The source is independent because it is not dependent on or controlled by any other voltage or current in the circuit. Okay, so that means that no matter what's going on in the rest of the circuit, you're turning on switches, you're unplugging resistors, you're plugging in other batteries, whatever's happening, if you have a truly ideal independent voltage source, because it's independent, its voltage does not change. So if I say this is 12 volts, it will always be 12 volts between its two terminals, unless you do something that theoretically contradicts it being 12 volts. You'll have some kind of conflict or contention there. Examples, realistic examples of ideal independent voltage sources, again with an asterisk, because this is only within certain bounds. But we often use ideal independent voltage sources to represent, for example, batteries. So this AA battery can be represented by this 1.5 volt voltage source. It's often how we represent it. In reality, a battery has some internal resistance. You use a Thevenin equivalent to model that. We're not going to talk about that right now. We're going to, but not right now. But it's often drawn in a schematic. If you have a 1.5 volt battery, just represent it with a 1.5 volt voltage source. An AC source example is a function generator. So you can set up the function generator in lab to be to do this, to create 5 cosine omega t, where omega is some kind of frequency in radians per second, t is time. You'd have a sinusoid created between these two terminals, and that's a realistic example. So if I have, like, I'm drawing a schematic and I want to just quickly put in a sinusoid, I could draw an independent voltage source like this. Okay. All right, so then let's move on to ideal independent current sources. An ideal independent current source maintains a specified current through itself. So here's its schematic symbol. It's going to cause, in this case, 5 amps to flow in this direction, and presumably to another part of the circuit. You can't have 5 amps flow into nowhere, so there has to be some other part of the circuit. So if I connect a circuit element, 5 amps will flow down through X, and you get the circulating current here. This is like a pump, pumping a constant rate of fluid flow. It has to go somewhere, and in this case, you would have circulating current like this. This current source is ideal because it maintains a specified current no matter what is connected to its terminals, except for an open. You can't have current flow out of an open terminal. But theoretically, everything else that's connected to it, right, will not affect its current. That's specified. It's independent because it's not dependent on any other voltage or current in the circuit. We'll contrast that with dependent sources in a minute. And so current sources are a little less, let's see, intuitive, because you can picture a battery with a voltage across its two terminals, but it's kind of hard sometimes to pick a practical example. But there are practical examples. For example, a constant current battery charger. Constant current battery charger can be represented like this, right? Within the bounds of where it's specified, where it can operate as a constant current charger. But for example, if you take one of these constant current chargers, you set it on 6 amps, you connect it to a battery, what's going to happen is let's say it's a 12-volt battery, the charger is going to cause 6 amps to flow, and the voltage across the battery is going to be whatever it needs to be. The voltage at the output of the charger is going to be whatever it needs to be to cause 6 amps to flow. So for a constant current source, the current is constant, but the voltage can change. For a constant voltage source, the current can change, but the voltage is constant. Okay, so this is a really practical example. Oftentimes for like lead acid batteries, you get these cheap chargers that say 6 amps and you connect it, and there's usually some upper limit of the voltage that it will output. But while the battery's charging, it acts like a constant current source. Okay, you can actually take a power supply that you have in lab and set it up as a current source, again within certain limits. But I can take a power supply in lab, I can set its current limit, I can turn up its voltage, and I can apply different components, a small resistor or a short or whatever, and the current will be constant, right? Okay. So so someone asks, why can't there be a closed loop with current? Let's see. There can be. Here is a closed loop with current. So that is flowing. Maybe stop by office hours. We'll draw out what you have in mind. And what are the small circles at the top and bottom of the node? Yeah. So these circles, they're just meant to be terminals, like someplace you might connect something. So oftentimes, instead of just drawing a wire with just ending the line, we'll put a couple circles or dots that say, hey, this is where you might connect something. Like here, I said, oh, I'm going to connect circuit element X. And before I connected it, I had 2 circles there. Okay. All right. So I've hit the end of class for today. So let's end this here. Don't forget, check out the assignments page on Canvas. The dates and the times are listed there. You have a few assignments coming up. Stop by office hours if you have any questions. See the Slack workspace. So if you have any questions, not during office hours, you can always post those to the Slack workspace. Thanks for joining class. I will start office hours in just a few seconds. So if you'd like to stick around, please do so. If not, I'll see you next time. Have a great night.